All right, welcome. This is Ralston Valley High School AP Chemistry's lecture series in which we're going to be looking at Chapter 11, Lecture number 3. We will investigate here properties of solutions, in particular vapor pressure of solutions and Raoult's law. Let's move on to our first slide. All right, so over the course of this lecture, we're going to be describing the vapor pressure of various different solutions. First off, we'll begin with a definition. We define vapor pressure as being the pressure exerted within a closed system by the vapor phase particles after equilibrium has been established between the liquid and gas phases at a particular temperature. And to understand how this works, let's go ahead and have a look at the manometers that we've got diagrammed on our page here. Imagine we take a look at this manometer on the left-hand side and notice, first of all, that this is a closed-ended manometer. And in this closed-end manometer, we're going to go ahead and put some mercury in the U-tube, which is going to separate the bulb from the other side. And recall, in a closed-end manometer, on the side opposite from where the bulb rests, we have a vacuum which is present. And then rather than placing a gas into the manometer, like you've seen during our gas laws unit, instead we're going to go ahead and put a liquid phase species. So let's imagine that it puts some water down here in the bottom of the bulb. Now recognize that water at a temperature below its boiling point will still have some molecules of water escape from the liquid phase into the gas phase. And this occurs again because temperature is a measurement of the average kinetic energy the particles have. Even though the particles on average are below the temperature necessary for all of them to transform into gas phase particles, that is, for the substance to boil, we will still see some of those molecules escape from the liquid phase into the gas phase because due to the random collisions within the system, some of those particles, due to those collisions, will end up with more kinetic energy than their neighbors. And as they get sufficient kinetic energy from time to time to escape the intermolecular forces of attraction that hold them into the liquid phase, in particular for water, that is, to overcome those hydrogen bonds, we would therefore see some of those water molecules escape into the vapor phase within our bulb. Now, as more and more of those molecules escape into the vapor phase, note that this is a reversible process. Those gas phase molecules of water can collide with the surface of the liquid water below them, and as such, they would be attracted to that surface via intermolecular forces of attraction, in particular hydrogen bonds, and therefore they could also return from the vapor phase to the liquid phase. So essentially, this phase change of water in the liquid phase turning into water in the gas phase is a reversible process, and as such will establish a point of equilibrium. Because those gas phase molecules inside of the bulb are moving randomly according to kinetic molecular theory, we would expect to see those molecules striking the surfaces of the container, and as they strike that surface, they will collide with it, exerting a pressure. The collective pressure of all those collisions pushing downwards on the surface of the mercury in the U-tube would push it up the other side, and we could therefore measure the pressure in units of millimeters of mercury off of this manometer, which would be, by definition, the vapor pressure of this water. Now, note here, folks, that the vapor pressure is temperature dependent. If I increase the temperature of the liquid phase water, more of the molecules will have sufficient kinetic energy to overcome the attractive forces holding them in the liquid phase, and therefore I expect to see the rate of evaporation increasing, leading to an increasing number of particles in the vapor phase, and therefore increasing frequency of collisions within of that bulb. And therefore I'd expect to see vapor pressures increase at higher temperatures. A substance which readily forms vapors is a substance which we refer to as a volatile species. This is different from the other places you might see volatile in the English language. Volatile in the English language is often used to describe unpredictable situations, but here in this context in chemistry, it means things that evaporate readily. Think like acetone, that's nail polish remover. If you've ever spilled acetone on the countertop, you've noticed that that acetone probably almost instantaneously vaporizes. It has a tendency to very, very rapidly evaporate. Now that's in contrast to a substance like, say, table salt. Table salt would be a substance we would expect to be relatively non-volatile. That is, it does not readily form vapors. We're familiar with it. If you spill salt on the countertop, it's just going to sit there. It's not going to evaporate off, forming salt gas in the air around you. Now, volatility, not surprisingly, is dependent upon the intermolecular forces of attraction between particles. The stronger the IMFs, the less volatile the substance has a tendency to be. That explains why salt, again held together by very, very strong ionic bonds, is unlikely to evaporate into the gas phase, whereas something like acetone, which is held together by London dispersion forces and relatively weak dipole-dipole interactions, would be likely to be a more volatile substance. All right, so we've had a conversation now about what it looks like to see the vapor pressure of a particular species. What about if we looked at a vapor pressure of a solution which was composed of a solvent and a non-volatile solute? Imagine dissolving salt in water. So let's have a look now at a second manometer. And in the second manometer, again, we're going to have the mercury column filling up our U-tube. And then on the left-hand side in our bulb there, rather than putting a pure water solution now, instead we're going to take some water and dissolve salt into it. Now remember, salt is a non-volatile component of this solution, and as such will not be escaping into the gas phase. If we were to zoom in very, very close here at the surface of that liquid, you would notice that at the surface, the presence of those non-volatile sodium ions and chloride ions essentially is going to block easy escape of the water molecules from the surface in those locations. And as such, you can kind of think about the addition of the solute as essentially diluting the solvent. With less solvent molecules present to the surface, we'd expect to see the rate at which the solvent escapes into the gas phase to decrease, and therefore we would expect to see at the equilibrium point a lower concentration of gas phase particles present in our system, and correspondingly a lower vapor pressure of the solution overall. So long story short, the vapor pressure of a solution composed of a volatile solvent with a non-volatile solute is generally lower than the vapor pressure of the pure solvent by itself. We'll have a look at the math behind this on our next slide. On our next slide here, we're going to have a look at what is referred to as Raoult's law. Raoult's law is the mathematical component of the conversation we had on our previous slide, which described the vapor pressure of a solution composed of a non-volatile solute dissolved in a volatile solvent. And to reiterate what we discussed on the last slide, for a solution which is composed of a solvent and a non-volatile solute, the vapor pressure of that solution is always lower than the vapor pressure of the pure solvent itself. And the justification being that that non-volatile solute essentially dilutes the solvent, leaving fewer of the solvent molecules present at the surface with enough sufficient energy to escape into the gas phase, and therefore a point of equilibrium where we have fewer molecules of gas phase species present in our system. Now, the math behind this is relatively straightforward. Raoult's law is formulated as following here. The vapor pressure of a solution is equivalent to the mole fraction of the solvent times the vapor pressure of the pure solvent. That is to say, if you think about a solution which is composed of, say, 50% non-volatile solute and 50% volatile solvent, the vapor pressure of that solution would essentially be half that of the vapor pressure of the pure solvent by itself. So essentially, it's a direct relationship. The vapor pressure of the solution increases as the mole fraction of the volatile component of that solution increases as well. And it's important to note here, before we move on to our next slides, that Raoult's law specifically defines the vapor pressure of a solution when one of the components of that solution is non-volatile. It's a more complicated scenario if we mix together two volatile components to form a solution. We'll investigate that situation on our next slide. All right, so on our previous slide, we introduced the idea of Raoult's law, which told us that the vapor pressure of a solution was going to be dependent upon the mole fraction of the volatile component of that solution multiplied by the vapor pressure of that pure volatile solvent. Now, in particular, a solution which follows Raoult's law is referred to as an ideal solution. An ideal solution is essentially a solution for which the mathematics described to us on this page hold true. They tend to form when the interactive forces, that is the IMFs that exist between solvent and solvent particles, solute and solute particles, and solvent and solute particles tend to be very similar to one another. So, long story short, what that really means is solutions behave more ideally the more similar the components of the solution are to one another. Now, the formulation of Raoult's law for ideal solutions can be derived essentially from Dalton's law of partial pressures and the definition we gave you of Raoult's law on the previous page. Recall that Dalton's law of partial pressures tells us that the overall total pressure of a system is equal to the partial pressures of the components of that system. That is, if we have two different species present in the gas phase, those are species A and B, the P total of the system would be equal to the sum of the partial pressure of gas A plus the partial pressure of gas B. Now, in formulating Raoult's law for an ideal solution, we find that the total pressure of the gas phase system is going to be equal to the mole fraction of the first volatile component, that is species A, multiplied by the partial pressure of that gas as a pure solvent, plus the mole fraction of the second volatile component, that would be component B, multiplied by the partial pressure of component B as a pure solvent. And note here, folks, that if one of these species were in fact a non-volatile solute, that would therefore essentially take this new expression we've derived here and simplify it down to the one we saw on our previous page. That is, if we saw, say, a solution which was composed of 50% of the volatile solvent A and 50% of a non-volatile solute B, then my equation would become the mole fraction of A, which would be 0.5, times the partial pressure of the pure solvent A, plus the mole fraction of species B, which would in this case be, again, 0.5, times the partial pressure of the non-volatile solute B, which if it's non-volatile would be essentially 0. And therefore, the pressure of the solution would be equal to the mole fraction of A times the partial pressure of that solvent as a pure solvent, which essentially is exactly the formula which we derived on our previous slide. So, in essence, what this equation is doing is essentially finding the weighted average of the partial pressures of the pure solvents themselves as a function of the mole fraction of the species which make up the components of our solution. That is to say, if the species is comprised more of species A than species B, then the overall pressure of the mixture would be more similar to the vapor pressure of the pure solvent A than it would be to the smaller component, species B. Or conversely, if the solution was comprised primarily of the volatile species B, then the overall total vapor pressure of our solution would be more similar to that of species B as a pure solvent than it would be to the minor component, species A. So it's essentially just a weighted average, which we're calculating here. So that's pretty much Raoult's law. On our next slide, however, we're going to see what happens when species deviate from this ideal behavior, that is, they do not follow this predicted weighted average calculation described by Raoult's law as closely as the math here would predict. Let's see that on our next slide. All right, so on our previous slide, we were introduced to how Raoult's law applies to solutions which are composed of two volatile components. It essentially told us that the vapor pressure of the overall solution was equal to the sum of the mole fractions of each component multiplied by the partial pressure of those components if they were pure solvents in the system. Let's see what happens now if we were to see deviations from this ideal behavior. Now, real solutions tend not to exactly follow Raoult's law as we'd expect them to. There tend to be deviations either to the positive side or the negative side based upon the attractive forces that exist between solvent and solute particles. So, have a look at our first graph. The x-axis of this graph shows the composition of our solution, with an increasing mole fraction of species A as we move to the right, and an increasing mole fraction of species B as we move to the left. The y-axis of this graph shows the vapor pressure of our solution. And you'll notice over here, if we are at the far left-hand side along that x-axis here, this would be a system in which the mole fraction of species A was 0, and the mole fraction of species B was 1. That is, this is a system which is entirely comprised of species B. The vapor pressure of that system would be the vapor pressure of pure species B, whereas the vapor pressure of species A, that is the partial pressure of species A in this system, would be at this point 0, as there's none of species A present. Conversely, over on the right-hand side of this graph, we would find now ourselves in the position where the mole fraction of species A was 1, and the mole fraction of species B was 0. And the vapor pressure of the system would therefore be equivalent to the vapor pressure of species A as a pure solvent. And you'll notice here that yellow line indicates the increasing partial pressure of gas A as the mole fraction of species A increases from 0 at the left to 1 on the right. And that other line there, which I'm assuming is some sort of magenta color, hopefully, is decreasing from left to right. That is showing the partial pressure of species B. On the left-hand side of our graph, we are seeing now the partial pressure of species B as a pure solvent, And on the right side, we see where the mole fraction of species B is 0. That would imply the partial pressure of species B is 0. And the third line on this graph, that is the blue line here, represents at any given point in terms of the composition of our solution, the sum of the vapor pressure of species A plus the vapor pressure of species B. That is the overall total pressure of our solution according to Dalton's law of partial pressures. So again, we can see here that at any point we choose, the sum of the vapor pressure of species A plus species B always equals the total pressure of that system given by that blue line up at the top. Now, this is a system which would perfectly obey Raoult's law. That is, the mole fraction of species A times the partial pressure of species A as a pure solvent, plus the mole fraction of species B times the partial pressure of species B as a pure solvent is yielding here the overall vapor pressure of our solution. Now, leaving that left-hand graph for a moment and considering instead the graph on the far right side, let's consider how we would see this system change or deviate from this ideal behavior if we were to mix together two particular species which I want to examine, which would be acetone and water. Now, both acetone and water are relatively volatile substances which have a tendency to evaporate into the vapor phase. Were I to make a mixture between acetone and water, I want to look at the intermolecular forces of attraction between particles within this particular solution. Now, importantly, water molecules are strongly attracted to other water molecules via the process of hydrogen bonding, in addition to their relatively weak London dispersion forces. Acetone molecules, conversely, have moderately sized London dispersion forces, as well as a dipole-dipole interaction which is present due to the polar nature of this molecule, due to the presence of that carbonyl group. However, acetone molecules cannot form hydrogen bonds with other acetone molecules, because even though there are hydrogens and oxygens present here, there is no place on an acetone molecule, which again is 2-propanone, where we'd expect to see a partially positive hydrogen atom present, because all the hydrogens are bonded directly to carbon atoms that have a very, very similar electronegativity to the hydrogen atoms in that bond. The oxygen, which would be required to form a hydrogen bond, is never bonded to a hydrogen, and as such, we do not see hydrogen bonds between acetone molecules. Now, that being said, when we form a solution here, consider what happens in terms of the IMFs between acetone molecules and water molecules. Whereas acetone could not form hydrogen bonds to itself, it can form a hydrogen bond to a water. That oxygen in the carbonyl group on the acetone molecule is an electronegative element, and there is a partially positive hydrogen on the water molecule, and therefore I would expect to see even stronger intermolecular forces of attraction between molecules of acetone and water than between the acetone as a pure solvent itself. And as such, as those hydrogen bonds form, this is going to essentially more strongly attract the acetone molecules into the solution than they had been before as a pure solvent. And it's these formation of these hydrogen bonds between acetone and water that would lead me to expect to find fewer acetone molecules in the vapor phase, as they would be more strongly attracted within the liquid itself. And therefore, I would expect to see what we would call a negative deviation from ideal behavior in terms of a lower vapor pressure of this solution than we'd expect to see through calculation via Raoult's law. Now, example 1 is asking me if the formation of this solution of acetone water would be expected to be exothermic or endothermic, and to justify our reasoning here. Given the conversation we just had about the relative strength of the IMFs attracting acetone molecules to water molecules, I would expect, as those acetone molecules and water molecules form those hydrogen bonds, the solution would find a position of lower potential energy. And as such, because we know energy is a conserved quantity, my expectation would therefore be that energy would therefore be released into the surroundings as those hydrogen bonds form, therefore making the process of mixing acetone and water a strongly exothermic process. So now we've seen how a negative deviation from Raoult's law would play out. Let's now consider what would happen in a different scenario. What about if I were to mix together two different components of a solution that were not at all strongly attracted to one another? Consider, say, the mixture of water and octane, that is the primary component of gasoline. Again, water molecules are strongly attracted to one another via the process of hydrogen bonding. Octane molecules are similarly strongly attracted to each other, but via strong London dispersion forces instead. Within water molecules, the London dispersion forces are very, very weak between molecules due to this small number of electrons present. So each of these components of the mixture are very, very strongly attracted to themselves. But the IMFs between the components of the mixture are very, very weak. The water molecules, with their very, very weak London dispersion forces, are not able to strongly attract the octane molecules via LDFs. And likewise, the octane molecules, with the complete inability to form hydrogen bonds to the water molecules, are likewise not strongly attracted to those water molecules. This is a system in which each of the individual components of the system are more strongly attracted to themselves than they are attracted to the other species in the solution. And now consider what would happen if I was to take octane and water and then thoroughly agitate the mixture to get the particles to essentially form a solution. Were this to occur, I'm essentially going to be spreading water molecules out away from each other, and in place of where there had been water molecules close together, causing the formation of those strong hydrogen bonds, I'm instead going to essentially insert octane molecules into those locations, which is going to essentially decrease the strength of those hydrogen bonds. And likewise, those octane molecules are now further spread apart from each other, now essentially being surrounded by water molecules. And as such, the LDFs between those octane molecules are going to be weakened as the distance between octane molecules on average increases. So because by doing this, all of the intermolecular forces of attraction are going to decrease between species, I'd expect to see, therefore, a greater tendency of those species to escape out of the liquid phase into the gas phase as they're being held by weaker forces into that liquid phase. And therefore, I would expect to see more gas phase particles present, and likewise, then, a increasing vapor pressure of the solution as a whole. So this would be what we would refer to then as a positive deviation from ideal behavior, where the observed vapor pressure would be greater than the vapor pressure of the individual pure solvents multiplied by their mole fractions as predicted by Raoult's law. So, in summary, in a system in which the components of the mixture are more strongly attracted to each other than the components are to themselves via IMFs, that would imply a negative deviation from ideal behavior and a lower vapor pressure of the solution overall than would be expected by Raoult's law. Conversely, for a solution which is composed of components which are very poorly attracted to one another via IMFs, we'd expect to see then a positive deviation from ideal behavior, because the IMFs within each individual solvent would be essentially disrupted by the presence of the other components of the mixture, thus weakening those forces of attraction and allowing more of the molecules to escape into the gas phase, leading to a higher vapor pressure than would otherwise have been predicted by the mathematics predicted by Raoult's law. And with these ideas now in mind, let's go ahead on our next slides and see if we can apply some of this math to work some example problems. So, working an example problem now for vapor pressures, let's go ahead and have a look here at example number 2, in which we are taking a solution prepared by mixing together 5.81 grams of acetone, that is C3H6O, with a molar mass of 58.1 grams per mole, and 11.9 grams of chloroform, chemical formula HCCl3, whose molar mass is 119.4 grams per mole. And we've got some given information here. At 35 degrees Celsius, the solution has a total vapor pressure of 260 torr. And we're going to be asked here, is this an ideal solution, given that the vapor pressure of pure acetone and pure chloroform at 35 degrees Celsius are, respectively, 345 torr for acetone and 293 torr for the chloroform. All right, so with this given information, let's go ahead and apply our Raoult's law. Recall, Raoult's law tells me that the vapor pressure of a solution is equal to the mole fraction of each component multiplied by the partial pressure of that component as a pure solvent, the sum thereof. So we're going to go ahead and need to calculate the mole fractions of our components of this system. And happily for us, they've given us some very easy math to work with here. We've been given here 5.81 grams of our acetone, that is the C3H6O. And a quick monorail here will allow me to calculate the number of moles of acetone represented here. There are 58.1 grams of acetone per 1 mole of acetone, yielding here a calculated value of 0.100 moles of the acetone in our system. Likewise, with 11.9 grams of the chloroform, that is HCCl3, a second monorail, will give me here a 119.4 grams of the chloroform per mole conversion factor. And yet again here, you'll see we calculate the same 0.100 moles of chloroform, essentially meaning that both components of the system are equal in their number of moles present, and therefore the mole fraction of each component would be clearly at this point 0.5. So we essentially have a 50-50 mixture of acetone and chloroform. With now our calculated mole fractions of each species, we can now go ahead and apply Raoult's law. So as our previous slide showed, the vapor pressure of the solution as a whole is equal to the mole fraction of each component multiplied by the partial pressure of each of those components as pure solvents, summed all together. For our system, that would be the mole fraction of the acetone multiplied by the partial pressure of acetone as a pure solvent, plus the mole fraction of the chloroform multiplied by the partial pressure of that chloroform as a pure solvent. So plugging in our given values then, our mole fraction of 0.500 for the acetone, multiplied by the vapor pressure given to me of the pure acetone of 345 torr, plus our mole fraction of the chloroform of, again, 0.500, multiplied by the vapor pressure of the pure chloroform of 293 torr, would yield an expected value of 319 torr for the vapor pressure of this solution. However, looking back to the given information in the problem, it told me that the vapor pressure of the solution overall was only 260 torr, implying, therefore, we have a strong negative deviation from the predicted vapor pressure of the solution via Raoult's law. So now that we recognize that, in fact, this is not behaving as an ideal solution, that is, not following the prediction from Raoult's law, let's see if we can come to understanding as to why it's deviating so greatly in the negative direction. Remember, a negative deviation from Raoult's law told me that there were stronger attractive forces between the components of the solution than within the individual components themselves. And so we need to justify why it is those acetone molecules are so strongly attracted to the chloroform molecules. So here, let's come up with a hypothesis. Within a sample of pure acetone, the IMFs present would be London dispersion forces, as well as a weak dipole-dipole interaction due to the presence of that carbonyl group, making this a slightly polar molecule overall. Within the chloroform molecules, again, we have London dispersion forces, and we would also have dipole-dipole interactions due to the strong dipole present due to those chlorine molecules and the hydrogen on the other side. So again, we've got a asymmetrical molecule there with differences in electronegativity, so therefore a significantly polar molecule. Now, importantly, what we don't see within any individual component of our solution by itself is the ability to form hydrogen bonds. However, when we mix these two things together, something kind of neat happens that we haven't seen here before. Looking at that chloroform molecule, I've got a central carbon atom bonded to 3 chlorines around the outside. And even though generally chlorine is not one of the elements generally associated with hydrogen bonding, remembering back to IMFs discussing nitrogen, oxygen, and fluorine as the 3 elements necessary to form a hydrogen bond, with 3 chlorine molecules all hanging out there on the same side of that chloroform molecule, we see the combined pull of all of those chlorines on the electrons within that carbon to hydrogen bond acting very, very similarly to an element like nitrogen, oxygen, or fluorine, which have very, very high electronegativities overall. And as such, we end up with a very, very partially positive hydrogen on that chloroform molecule. And because there's a strongly partially positive hydrogen hanging out there, as well as on the acetone molecule and oxygen as part of that carbonyl group, I would expect to see an uncommonly strong attractive force between that oxygen and the very, very partially positive hydrogen. Essentially, we were able to form a hydrogen bond here, even though there were no nitrogen, oxygen, or fluorine present on the chloroform molecules. And because that attractive force between the components of our solution is greater than any of the attractive forces within any individual component, therefore, there's going to be fewer of the molecules likely to overcome those attractive forces and escape into the gas phase, and we would therefore see a lower overall vapor pressure of our solution, justifying then the negative deviation from Raoult's law, which we've observed in our math here in this system. So a real tricky application here, but makes logical sense. Let's move on to our final slide. All right, for our final example given in this lecture, we're going to look at example number 3, which is asking us which of the following would be expected to have the lowest total vapor pressure at a temperature of 25 degrees Celsius. And the 4 different solutions they're going to ask us to consider here are: number 1, pure water with a given vapor pressure of 23.8 millimeters of mercury at 25 degrees Celsius. Number 2, a solution of glucose in water where the mole fraction of glucose is given as 0.01. Number 3, a solution of sodium chloride in water where the mole fraction of the sodium chloride is given as 0.01. Or number 4, a solution of methanol in water where the mole fraction of methanol is given as 0.2, where the vapor pressure of pure methanol is listed as 143 torr at 25 degrees Celsius. So, with those as our 4 choices, let's go ahead and start by eliminating some possible options. The first thing I'd like to eliminate is option number 4. That is the solution of methanol in water. Recognize that methanol is a more volatile solute than water is itself, given its higher vapor pressure than water at this particular temperature. And therefore, I would expect to see the vapor pressure of this solution to be somewhere in between the vapor pressure of pure methanol and pure water, as both of these components are themselves volatile. And as such, I could simply apply Raoult's law here to determine the actual vapor pressure of the solution, which is expected to be greater than the vapor pressure of pure water. So again, to find the vapor pressure of that solution, I would take the mole fraction of my methanol, which again is given as 0.2, and multiply that by the vapor pressure of pure methanol, given to me as 143 torr, and then add that to the mole fraction of my water, given as 0.8, multiplied by the vapor pressure of the pure water of 23.8 torr. And when I perform this calculation, Raoult's law here gives me a vapor pressure of 53.2 torr, as I expected, greater than the vapor pressure of my pure water, so I can eliminate that last option. So that leads me now to consider one of these first 3 options, which must have the lowest vapor pressure. Now, kind of taking pure water as the baseline, consider the 2 middle options there. Those are the solutions of glucose and salt in water. Both glucose and salt are non-volatile solutes, which might lead me to initially believe that they would have the exact same vapor pressure as the mole fraction of those solutes are the same at 0.01. Consider for a moment, however, the difference in how each of these 2 species dissolve. Glucose, as it dissolves molecularly due to the presence of covalent bonds between all of the atoms present in this system. Whereas the sodium chloride, being made up of sodium ions bonded to chloride ions, would dissolve via the process of dissociation. Again, those polar water molecules would cause the sodium ions to dissociate from the chloride ions as they enter into the solution. And importantly, as I note that, what that really means is, as the salt dissolves in water, even though the mole fraction of the salt is the exact same as the mole fraction of the glucose, the mole fraction of the ions, that is the separate sodium ions and chloride ions combined together, would be greater than the mole fraction of the glucose because one salt molecule upon dissociation would actually yield 2 ions in solution. And this is essentially an idea we're calling here a Van 't Hoff factor. That essentially tells me about the number of particles in solution that are formed via the dissociation process. The Van 't Hoff factor for glucose is 1, that is, it dissolves as the unit molecule as a whole. The Van 't Hoff factor for sodium chloride is 2, meaning it produces twice as many particles in solution, and the addition of those additional ions upon dissociation would essentially occupy more positions within the solution, leading to a further decrease in the mole fraction of the water overall. And as such, I would expect to see a larger decrease in the vapor pressure of the saltwater solution than I would of the glucose in water. So long story short, the more particles that form as the species dissociate, the larger the mole fraction of the solute becomes as we end up with more particles of solute present in the solution, and therefore the smaller the mole fraction of the solvent, leading to, by Raoult's law, a decrease in the vapor pressure of the solution as a whole. So therefore, I'm going to go ahead and choose here the solution of sodium chloride in water as the solution with the lowest vapor pressure under these temperature conditions. All right. So that is it for our discussion of vapor pressures of solution, and that is also it for all of Chapter 11. Thanks for listening. We will see you at our next chapter.